Hello, my name is Necati Cihan Cemgöz, and I'll be presenting our most recent work, Sign Language Transformers. This work was done in collaboration with Oscar Kohler, Simon Hadfield, and Richard Bowden. In this work, we are tackling two vision-based sign language tasks, namely continuous sign language recognition and sign language translation. In CSLR, the goal is to predict sign gloss sequences from videos. However, in SLT, our aim is to translate sign sequences into spoken language sentences. As you can see, there is not a one-to-one mapping between sign glosses and spoken language words. This is due to each language having their own unique vocabulary, grammar, and linguistic rules. In our previous work, Neural Sign Language Translation, we used RNN-based attention techniques and investigated different translation setups. Sign-to-text was the first end-to-end approach where the spoken language sentences were directly translated from continuous videos. Although it was able to produce meaningful translations, the overall performance was quite poor. To address this, we introduced sign-to-close-to-text approach, where we divided the translation task into two steps. We used the state-of-the-art CSLR model as the sign-to-gloss step, which required gloss-level supervision. Then we realized SLT using a text-to-text translation model by mapping sign-gloss sequences to spoken language sentences. This approach significantly improved the translation performance. However, it imposed an information bottleneck as glosses are incomplete, text-based representations of multi-channel visual signs. One can consider the second, gloss-to-text step as trying to translate from a source language without having access to its grammar. To utilize gloss supervision without limiting the learned representations, we proposed sign language transformers. We trained the transformer encoders using gloss annotations to recognize sign sequences from continuous videos. As we are utilizing CTC loss function, we do not require frame-level gloss alignments. We then passed the learned spatiotemporal representations of the signs to transformer decoders, which are trained to generate spoken language sentences one word at a time. Our models are jointly trained using a weighted sum of the recognition loss and the translation loss in an end-to-end manner, thus solving two sequence-to-sequence problems simultaneously. We evaluate our approach on the Phoenix 2014 T corpus. It contains broadcast interpretations of weather forecasts from 9 signers. We consider 3 setups, namely sign-to-gloss, sign-to-text, and sign-to-gloss-on-text. Sign-to-gloss is essentially continuous sign language recognition. Sign-to-text is the direct translation to spoken language, and finally, sign-to-gloss-on-text is a combination where the models were jointly trained for recognition and translation. We utilize 2 metrics in our evaluations: word error rate for recognition and below scores for translation. We first look into the special embedding layers and conduct several experiments in sign-to-gloss setup. We use ImageNet features from 3 variants of efficient nets and CNN features from a state-of-the-art CSLR model. In comparison to efficient nets, CSLR features achieve better recognition accuracy, thus displaying the importance of pre-training. We also discovered that the transformer networks are sensitive to their input scale. We utilized batch norm to scale features down and ReLU to add more nonlinearity, which significantly improved our recognition performance. Next, we conduct experiments to find a good balance between the CTC-based recognition loss and the verb-level cross-entropy translation loss. In our experiments, weighting the recognition loss with a scale of 5 gave the best overall performance, which compensates for the scale differences between losses. Furthermore, training our models jointly on both tasks improved their performance. We believe this is due to losses regularizing one another, while recognition also aiding the encoder for translation. Our approach achieves state-of-the-art performance in both video-to-text recognition and translation. In sign-to-text setup, we double our previous translation accuracy. To underpin future research, we also conduct experiments on text-to-text translation setups. We report improved translation performance over the previous RNN-based attention models. In conclusion, sign language transformers introduce a new way of realizing SLT. Overcoming the two-step approach, our multitask framework achieves state-of-the-art performance across all baselines. We also showed that the joint learning benefits both recognition and translation. One interesting observation is the transformer's sensitivity to the input scale. Although we have reduced the need for detailed gloss alignments, gloss annotation is still required, and this is a limiting factor for realizing large-scale SLT. To address this, we are planning to focus on sign articulators and other building blocks of the sign, such as subunits. Thank you for listening. Our source code, models, and qualitative examples are available on our GitHub page.